Alright, so in this video I'm gonna be explaining another important article with the title Tackling Oversmoothing in GNN via Graph Sparsification, a trust-based approach. So this paper in 2024 from Georgia State University. Graph neural networks achieved great success for node-level and graph-level tasks via encoding meaningful topological structures of networks in various domains, ranging from social to biological networks. However, repeated aggregation operations lead to excessive mixing of node representations. By the way, this aggregation operator is a low-pass filter. That's why when your graph is heterophilous, then you need to augment it with the high frequency. So, for example, Laplacian to be the high frequency counterpart, and the adjacency is the low frequency. So we have two channels. That is a new idea, not new idea since 2020, that we can avoid oversmoothing for heterophilous graphs. But in general, it's still there are many ideas for oversmoothing. But oversmoothing is very well understood. So, but the harder problems are oversquashing, which is not mentioned in this paper. So this phenomenon leads to oversmoothing that hampers downstream graph analytic tasks. So to overcome this issue, we propose a flexible trust-based graph sparsification that prunes edges from dense regions of the graph. Pruning redundant edges in the dense regions helps to prevent aggregation of excessive neighborhood information during hierarchical message passing and pooling in GNN models. So the baselines of explaining graph isomorphism, sag pool, diff pool, min cut pool, daemon pool, I've explained these in different videos. So this is an early oversmoothing that average node representation distance of different K-trust subgraphs concerning GNN layers. And this is ESM of toy graph and sparsified graph. So we observed the prior stationary representation learning of node emerging in network's high trust region, which denotes a new perspective when explaining oversmoothing. In edge pruning step, we measured the two nodes' average neighborhood trustness to detect the regional interconnectedness strength of the nodes. And we develop a simple but effective model by pruning noisy edges from graph based on their node's average neighborhood trustness. So the core of this idea is the trustness, a neighborhood trustness. So the aggregation and update in message passing in any graph neural network. Then for pooling, you need to get a readout because you need to summarize them. And there are many approaches for pooling. For example, they use a scoring-based approach to get top K nodes. But clustering-based pooling methods from super nodes by grouping original graph nodes that summarize the node features. For example, a cluster assignment S that you are familiar with in diff pool or min cut pool or many other ideas in hierarchical graph pooling. And then they talk about the problem of oversmoothing, that two nodes very close to each other have the same representation. But let's see what is the problem. We are given some vertices, edges, and some features. We call this attributes. Here they call it feature matrix. Because we have n nodes, each node has d-dimensional attribute vector. Then the neighborhood of a node u is denoted of n of u. So for a data set D consists of a set of graphs, and they have labeled, so it's a graph classification. Our trust-based sparsification introduces a set of sparsified graphs. Now these are the sparsified graphs corresponding to this. And this algorithm is designed to remove redundant graph connections and retain the graph's essential structural information. So they want to remove some connections to see if they still can predict the appropriate labels of each graph. That's a good idea. It's also related to interpretability. It's also related to robustness. It's also related to attack. And so there are many areas that are related to this interesting idea. But what is K-trust? If you ask ChatGPT, it says it's a concept from graph theory that extends the idea of a traditional trust. In a K-trust, a subgraph is considered a K-trust if every edge in that subgraph is part of at least K triangles. So, key points. Triangles. The fundamental unit of a K-trust is a triangle. If this is triangles, and then a K-trust emphasizes the importance of local connectivity within the graph. For example, K-trusts are useful in social network analysis, biology, transportation networks. So the concept generalizes the idea of a triangle, which is a three truss, to higher values of K. A one truss is simply a collection of edges, while a two truss requires that every edge be part of at least two triangles. So finding K-trusses can be computationally challenging. Then they defined this support. The support of an edge is the number of triangles where E involved. Then K-truss subgraph. So this is very much about structure of a graph, local structure. How does it look like? Which is often overlooked in the literature. So we emphasize, we explain the proposed trust-based graph sparsification model to overcome oversmoothing problem for graph classification. So in phase 1, we compute edge trustness. We apply K-trust decomposition to compute its edges trustness as weights. Next, we split all edges into groups based on their trust values. High trust edges and low trust values for a given threshold eta. Then we measure node strength. It focuses on high trust edges for sparsification. As high trust edges have higher degrees, they massively contribute to the oversmoothing phenomenon. Then we have prune and update. When the minimum value exceeds the standard density assuring threshold, we prune the edge from the graph and update all edges trustness values. And then learning. At the end of the sparsification, we first feed the processed graph to GNN for graph learning. But the core idea is dense region identification. To learn the structure of the graph, GNN applies message passing. Through repeated message passing nodes, so dense regions get similar neighbors, which causes oversmoothing. As a result, the features of those regions nodes become indistinguishable. Many different. That's why in heterophilous graph, if they talk about aggregation operator, all of us know, but they also talk about diversification of it. This is related to high frequency, like Laplacian. Disaggregation is related to adjacency. So that if we have two channels, then we can come up with the heterophilous graph. So let's carry on. Our approach employs a trust decomposition to compute edge trussedness and discover all K trusses from G. At first, it takes an unweighted graph as input and computes the supports of all edges. Then, initialize the value of K as 2 and select the edges with the lowest support. Next, the value is assigned as edge weight and the edge is removed. So first we have 4 phases, as I said. First, edge truss, and then node strength. Then we prune and update it. Finally, we learn so that we can understand the label of that. But this one is computationally expensive. It's a different problem, totally. It's for itself is a project. And high truss edges, pruning redundant edges. The strength of a node is measured as a summation of all its incident edge weights. However, in this research, node strength is applied as the average of nodes' incident edges trussedness. For a candidate E, after measuring the node strengths, this minimum value has been taken. And finally, after removing the edges and then going through this loop again, then we have the output, which is a graph where edge trussedness is T for each edge. So we get the graph, truss graph. And then after that we do sparsification by edge guide and reducing the high truss. So very algorithmic. So they did for these benchmarks are for graph classification. As you see, most of them have only 2 classes because it's very hard for graph classification. It is still much harder than node classification. Oh, I cannot say that because heterophilous graphs, the baseline score is 46% for that funny data set. What was the name? Too funny data set is the name of a bird. So state of the art is just 52%, 40. So it's room for improvement for heterophilous graphs. But graph classification is still challenging. Even for these simple data sets like proteins, state of the art is less than 95%, less than 90%. So these are baseline, diff pool, daemon pool. I've explained all of them in the current playlist. So biomedical dataset, social network dataset, different properties. They have very different properties. Protein for different baselines.